Okay, so I think we can start. So till now in this course we have talked about techniques for reliability analysis. The first category is non-sampling based approaches, Taylor series based based methods, or you can even call them analytical approaches, where the idea was that you will try to find the point on the limit state surface that is nearest to the origin in the standard normal space, and that point is known as the most probable point, design point, most probable failure point, and all of those things. And then you will construct a lower order approximation of the limit state function. That lower order can be first order. In that case we call it first order, and in that case we call it the second order reliability method, right? So one of these things you can do, and then you can find out the reliability, right? The second category of methods that we have discussed is sampling based approaches, which is primarily based on the law of large numbers. And the idea is you will draw sample to approximate the integration that gives you the probability of failure. The obvious way of doing it is to use Monte Carlo integration, in which case you will call it the Monte Carlo simulation. But that has a very slow convergence. The variance reduction is very slow, or variance is high. And so we have variance reduction techniques such as importance sampling, where you decide to sample from another distribution such that the variance is reduced. And even if you don't like that, for rare event there is subset simulation, and in subset simulation you decompose the failure event as product of multiple event having larger probabilities, and then you compute the failure probability as product of those. So these are broadly speaking the two category of methods that we have talked about, right? So the first thing that we have talked about is non-sampling based approaches, which is primarily based on Taylor series, right? Finding the most probable point and then constructing an approximation based on Taylor series. Okay, so these are based on Taylor's series. An example include if first order second moment, and within first order second moment you have the advanced first order second moment, which is the form, and then you have the SORM, and there can be HORM also, higher order reliability method, but we did not talk about it. I said that if you are interested you can go ahead and read about it, but we will not discuss it in this course. Okay, we will only discuss the popular ones, right? And then after non-sampling based approaches we proceeded with sampling based approaches. Sampling based approaches and in sampling based approaches you have, for example, we have talked about Monte Carlo simulation, MCS, which is the most obvious one. Then we have talked about importance sampling, and we have talked about subset simulation, right? And all of these are based on how you are looking to approximate the integral of the limit state function in the failure domain, right? Now, similar to non-sampling based approaches where form, SORM, FOSM were not the only methods, even in sampling based approaches, Monte Carlo simulation, importance sampling and subset simulation approach are not the only approaches. There are other sampling based approaches as well. For example, there is something known as the directional simulation. There is something known as the Latin hypercube sampling. And both of these can be used for finding out the probability of failure as well. But we will not be discussing either of this. We will not be talking about Latin hypercube sampling, and we will not be talking about the directional simulation, primarily because the idea of this course is to introduce you to the approaches and introduce you in depth to some of the approaches. Now, what will be this sum? This sum will be those which are the most popular ones, which are the most used ones. And importance sampling, Monte Carlo simulation, subset simulation, these are the most used ones, right? And that's why we talked about these three only. But if you are interested again, you can go ahead and read about directional simulation, you can read about Latin hypercube sampling. Okay? So, you now have the knowledge base to go and study those on your own. That is what I basically mean when I say that you can study those now based on the knowledge you have gained by studying MCS, IS and SS, and by studying probability theory at the beginning, and by studying non-sampling based approaches before sampling based approaches, right. Now, among these two approaches, if we have to compare these two approaches, what are the strength of these approaches and what are the weakness? Obviously, none of these methods are perfect, because then we would not be discussing the others, we will focus the total course on that. So, none of these are perfect, all of these have their own limitations. But when I say what are the limitation and strength, I mean in a broader sense. So, for example, what will happen if we compare non-sampling based approaches versus sampling based approaches? So, if I have to compare non-sampling based approaches versus sampling based approaches, and now all of you have studied both of these methods already. So, let me ask you, we will compare it on different aspects, right. Let us talk about, first of all, from technical or methodological point of view. From methodological point of view, how does non-sampling based approaches work? And Taylor series based. So, Taylor series and design point, these are the two keywords of non-sampling based approaches, right. So, the two key points will be Taylor series and MPP, right. For sampling based approaches, what will be the highlight? It is based on sampling, obviously the names, law of large number, you can think of that, right. Okay. Law of large number. So, it is methodologically it is based on law of large number, because you have to keep in mind, even when we are decomposing the failure probability into subsets, each of those subsets we are evaluating based on the law of large number, right. So, broadly speaking, you can imagine that this is based on law of large number. Okay. So, this was based on methodological point of view. Let us go one step ahead. Out of these two, which do you think is faster? You have not yet coded sampling based approaches, but in general, which method do you think will be faster? Depends on number of design points. What is design point? Design point is MPP. So, which is faster depends on number of design point. IS might depend on number of design point, because IS you are forming the local importance sampling at the design. I mean, for subset simulation, how does design point come into it? So, which do you think is faster? No, non-sampling based approaches are the faster, significantly faster. You will realize non-sampling based approaches, even in the worst case scenario, will take maximum 500 to 1000 samples, because it is iterative, and any optimizer you run it for 500 to 1000 and then you say it is not converging, you will stop it. In that case, it might not be accurate, but it will not give you any benefit in running it more than 1000 iterations. So non-sampling based approaches are significantly faster. In fact, they are the fastest in most cases. So it is much faster than sampling based approaches. Because in sampling based approaches, you are looking at very large number of samples. Even when you are doing subset simulation, you might, because for each of the subset also if you use 500 samples, so even in that case you have to evaluate the limit state function, right? So you are looking at very large number of samples. Okay, so non-sampling based approaches are faster, much faster than sampling based approaches. Again, when I'm saying it is faster, you have to let it increase, but in most cases, how will you compute the gradient? I talked about finite difference, but in reality, you do not use finite difference. The best way of computing gradient is to formulate the adjoint. And when you compute the gradient by using adjoint based method, that is quite fast. Okay. And in many cases, you might know the adjoint. And lastly, if the number of variable increases, actually apart from MCS, nothing can be used. If I increase this number of variable dramatically, nothing can be used except MCS. So we are not talking about number of variables. We are saying that in a generic problem, which one will be faster? When I say generic problem, even for 2 variable, 10 variable, 20 variable, and all of those things. There are always special cases, but generally speaking, non-sampling based approaches are much faster than sampling based approaches. Okay. So this is faster, whereas sampling based method is slower. Okay. Now again, when I am slower, remember that I am talking about sampling based approaches in a generic sense. Within sampling based approach, we know that MCS is the slowest. IS and SS are faster than that. But here I am comparing the two categories and not specific methods. Which one is more accurate? Sampling based. Okay, sampling based method is always more accurate, and in fact it can give you theoretical guarantee if you draw infinite number of samples in that case, right? So you know, so this is more accurate. More accurate. This is less accurate. Now again, remember, when I am saying less accurate, I am talking about generic problems. If it is a linear limit set, this is exact. I mean, those are special cases. Generically speaking, or rather I should say statistically speaking, statistically if you solve a million reliability analysis problems, statistically sampling based approaches are more accurate. But it does not mean there cannot be a problem for which non-sampling based method is not accurate. It will be if it is linear, for example, it will give you exact, right? So keep that in mind. When I am saying this, I am talking about in a generic sense. There will always be exceptions. Okay. Okay. Now from this table, what can we conclude? That none is perfect, neither is perfect. Both have its own limitation, both have its own advantages, and you should select it based on the problem at hand. If you know the limit state function is linear or weakly non-linear, you should use non-sampling based approaches. If you know that the limit state function is very fast to sample from, you should use sampling based approaches, and all of those things, right? But can we not have something which is somewhere in between, which is probably less accurate than sampling based approaches, but more efficient than sampling based approaches, which is more accurate than non-sampling based approaches, but potentially less efficient than non-sampling based approaches? We are trying to look at something that resides at the middle. That means, can there be something that is somewhere between sampling and non-sampling based approaches? And there is, and that is the third and last category of method in component reliability analysis. So I like to highlight at this point that we are only talking about component reliability analysis. Why am I highlighting it now? Because this is the last category of method for component reliability analysis. After that, we will go into system reliability analysis. So this is the right time that I bring this term component into picture. Okay. So the third category of method is known as the surrogate based approaches. Surrogate based approaches. Okay. So the basic idea of surrogate based approaches is that it tries to address the computational cost of sampling based approaches while compromising somewhat on the accuracy. Okay. Now, for a minute, go back and think about sampling based approaches. Why are sampling based approaches computationally expensive? Why more number of samples make it computationally expensive? That is the actual question. Let's put. The limit state function is expensive to run. If I have to say it like that, more number of samples is a problem because the limit state function is potential in form of a finite element solver or a CFD solver or a FSI or a DFT or a molecular dynamics, something like that. And these simulators, and now I am bringing this term simulators, all of these are simulators, right? These simulators are expensive to run. A single simulation takes lots of time, right? So surrogate model addresses this issue. Surrogate model, the high level idea is that it tries to build a model, an alternative model to this expensive high fidelity simulator. And this alternative model is known as the surrogate model. Surrogate means replacement. So this becomes a replacement model. Okay. And now once you have this replacement model, you can now use that replacement model to do sampling, which means you will now run MCS over that approximate surrogate model. Okay. So to write it, the high level idea here is that the high level idea is to build a surrogate model, which is, by the way, surrogate model has many names. I will just give you 3 names. Surrogate model is also known as meta model. So in some paper you will find a name meta model. It is also known as emulator. So build a surrogate model, or you call it meta model, or you call it emulator. So the high level idea is to build a surrogate model that replaces the original limit state. Right? This is the high level idea. So in this case, how will you write it down? How will you evaluate PF? Your PF hat was equal to, PF hat was the one you were getting using sampling. This was equal to 1 by n summation I equal to 1 to n, the indicator function, and then g of xi less than 0. This is what it was. Now this gxi is my limit state function. So you can imagine this gxi to be a very expensive simulator. So what will you do? We will replace this gxi with g hat xi, which is hopefully an approximate but quick model. So this is then approximately equal to 1 by n summation over I equal to 1 to n, indicator function, g hat xi less than 0, right. Right. So this is what you will do in a surrogate model. You will try to build this g hat x or g hat which is a replacement for this g, and then use g hat to compute probability of failure. Now you can ask that, okay, can I not use this g hat for running my form or swarm? Yes, you can. But then if this g hat is really fast, why should you do that when you know sampling based approaches are more accurate? So there is no point in running form and swarm over this g hat, but in practice you can. No one will stop you. And if needed, you can always resort to that. But in general, because this is very fast, you can always sample a million samples or a billion samples. It should be very fast. And so there is no need as such to use form and swarm, but you can. You can always take this g hat into the limit state, find the minimum distance, then do an analytical approximation. You can always do that, but it's not needed in general. Okay, clear? So what is the most important part in surrogate model then? To construct this g hat. To construct this g hat is the single most important aspect in surrogate modeling approaches, which is very simple, right? So therefore, the single most important aspect in surrogate modeling, so I will write it SM, is to construct g hat x, right? Now, what do you think a perfect or an ideal g hat x? What are the properties of an ideal g hat x? Can you tell me which will be an ideal g hat x? G hat x should match gx as closely as possible. But is that all? Is there anything else that you can think of apart from that is correct? The first criteria should be that it should match gx as closely as possible, because that will give low cost. So it should match gx as close as possible, but it should be fast. You should be able to run it a million times or a billion times. Second, correct. Anything else? Accuracy you already mentioned. So that was accuracy, right? It should match gx. So accuracy. The second one was that it should be fast. Otherwise, why will I use it? If it is a very expensive one, I will not use it, right? I cannot use it rather. Anything else? How will you get g hat x? What do you think? What do you mean by that? Memory requirement of what? Yeah, what do you mean by modeling of that? That's what I was asking, right? How will you model g hat x? How will you get this g hat x? That's what I was asking. Integration. Regression. So one option is that it will be a regression model, right? So it will be some regression model, right? Correct. So now, how do you get a regression model? Already available, but can you use it on the, just take it and use it for making prediction, or do you need to do something? Train. So this g hat x, if you think of it like a regression model or a machine learning model, it is a machine learning model. So you will need to train it, right? And how do you train it? Data. How will you get the data? By running gx. So are you okay if a model needs a million points to train? No, right? So you will want your model to be capable of getting trained from as few training samples as possible, because it is the training sample generation that will contribute to your computational cost. Because just imagine that your problem is a fluid structure interaction problem. A single simulation takes 1 day. Okay. So if you have to generate 1000 simulation, it will take 1000 days. Assuming parallelization and all those things, let's say it will take 100 days. 100 days to generate training data. How many? 1000. How long will the model take to train? Even GPT-like model takes close to a month to train. Now compare close to a month with 100 days. Your normal regression model will take few hours at best, in some case few seconds to train, right? So this training cost is actually going to be negligible compared to the time required for generating the training data, correct? And now let's talk about inference. Well, you have your model. You are now using your model to make predictions with a regression-like model, machine learning model. How long the prediction takes? You can make 1,000,000 prediction in a second or in few seconds. You will just parallelize it and send it, right? So that prediction or inference time is also negligible. So what is the major cost of in surrogate model? Generating training data, which is generated by running the simulator, which means what should be your objective? That your model should need as few data as possible. So to summarize, what are the three conditions that this surrogate model should satisfy? An ideal surrogate model should satisfy. It should be accurate. G at x should be as close as possible to Gx, right? It should be fast to sample from. That means the inference time should be very fast. And thirdly, data requirement should be less. You should be able to train it from as few data as possible, right? So an ideal surrogate model should be accurate. It should be accurate as possible, or closely resemble Gx, right? Which means closely resemble Gx. It should be fast, actually extremely fast during prediction, right? And thirdly, should be I have already written, trainable from very few training samples. Right? Clear? And now you should be able to appreciate that if the number of training sample is less than the number of iterations required in form, then this will be even be faster than form. But in most cases, the number of iterations required in form is lower, because in the problem we have solved, it was what, 7, 10, something like that, right? So it's lower than the number of samples needed for surrogate model. So in that case, it becomes costlier than non-sampling based approaches. And you should also be able to appreciate that it is always faster than sampling based approaches until and unless it requires 1,000,000 samples to get trained, right? Is it clear? Any doubt on this? Okay. So now, so these are the ideal thing, right? Now, what are the steps involved? Today we will not talk about any surrogate model, any specific surrogate model, okay? That will start from next lecture. By the way, before I forget, let me tell you one thing. The syllabus for minor will be until what I have covered today. Wednesday and Thursday I will take lecture, but whatever I cover is not included in the syllabus for minor. So until whatever I will cover today, that becomes your syllabus, okay? Which means just introduction to surrogate model and then sampling based approach in detail, non-sampling in details, probability and statistics, and limit set function and all those things, right? So the syllabus is until whatever I cover in next 20 minutes. Okay. Okay. So now coming to a generic steps involved in training a surrogate. What do you think is the first stage? Step. I am not writing an algorithm, just step. What is the first step? Generating training samples. How will you generate training sample? By running simulation. But before running simulation, you need to generate sample of your input. So the first step is generating sample for x, which is my input. Generate x I equal to 1 to nt. N I cannot use, n is number of samples I use in Monte Carlo simulation. So, I use the term nt, maybe small t, where nt is my number of training samples, okay, which needs to be minimized, by the way, keep in mind. Okay. Step 2 is, it is a supervised learning technique, although this is not a machine learning course, but you can understand its regression is a supervised learning technique. So, which means you will also need the label, which in this case is y, the limit set function, right. So, you will evaluate y I is equal to g of x I for all I. Now, here at this stage I would like to mention something. Often the threshold or in your limit state function is a constant, often, not always, but often. So, if the threshold in your limit state function is constant, we often only train for the portion excluding the threshold. So, if g of x I is equal to g, I mean some threshold minus g hat of x I or g tilde of x I, we will only train for the g tilde of x I. Why? There is no specific reason, but your finite element solver is giving you that, and that is the reason. But if your threshold is probabilistic, that means it is part of x, in that case you have to train for g of x I. It is not that the results will vary, you can use either, but that is generally what is done in many cases. Okay. I will repeat what I said. So, what I said is that if your threshold is a constant, in that case you train the surrogate model, it is of normal practice, there is no advantage to that. You train the surrogate model to predict the response, threshold minus response is your limit state, right. So, you just predict the response or demand C minus D. Okay. But if the threshold or capacity is random, then that is a random variable, that is part of x. So, you train for the total g of the limit state function. Okay. But again I will repeat, there is nothing wrong in always training for the limit state function, you can do that. What I am saying is a common practice, but does not mean you have to follow that. There is no advantage to following that in most cases. So, anyways, coming back, step 2 is you will find out the labels. Step 3 is you will train your surrogate model by minimizing some statistical difference between what your surrogate model is giving and what is the actual y you got from the step 2, which is simulation. So, step 3 is train the surrogate model by minimizing the difference between, and this difference is a statistical difference, you can imagine it like a loss function or it can be like a likelihood and all of those things, which we will discuss when you go to surrogate model. Difference between the surrogate predicted response surrogate predicted response and simulated and response obtained from simulated responses obtained from simulator. This is my step 3, and step 4 is solve the reliability analysis problem by using the surrogate model, which is with MCS or whatever you want, right. Step 4 is solve the reliability analysis problem, which is these are the obvious steps. I mean, there is nothing new or nothing difficult in these 4 steps. These are like the obvious thing that will come to your mind even if you don't attend the course, right. These are the obvious things. But what might not be so obvious, or might be, I don't know, which among these 4 steps do you think are the most important? 3 and anything else? So, one is generating X, second is evaluating Y, third is training, and fourth is solving RA. So, out of this 3 you said is important, and that is correct, because that ensures that the surrogate is accurate and all those things, right. So, it is correct. What else? That is the most time consuming one, but you cannot really do anything with that because G is given to you. Generating X, why is that?
Taking that is going to train our surrogate.
Correct.
So if that is not good enough, then we will not get it.
Correct. But now you have to define what do you mean by good enough. Because yi will be good enough because G is exact or existing. Overfitting will come in step 3. Training, you put a regularizer and ensure that is not overfitting. So that is part of step 3. Yes. Model should have low uncertainty, true. But how will the model will have low uncertainty? Correct. Correct. So we were saying that I should sample in such a way so that it extract the maximum information.
We are deciding the number of training samples.
We are deciding, yes, but that need not be decided there. You can do an iteration and to decide it also. Not true, because if you only can be true, but need not always. Suppose you train the surrogate model so that there are more number of failure points. That means the surrogate has only learned the failure zone. In importance sampling, that was needed because you are using the actual G. There was no approximate G there. Now there is an approximate G. Now imagine what will happen if you have more samples near the failure zone and almost no samples away from it, let's say. So what will your model learn? It will only learn in the failure area. Now during step 4, you will solve the, do it using MCS. In MCS, many samples will come away from that. That's MCS, right? It will generate everywhere based on distribution. Now your G hat will give wrong results for those away from that. And if it is very wrong and start classifying a failure as safe, your probability of failure will go wrong. So that means you want your surrogate to be accurate near the failure surface, but then you are assuming that away from it, even if it is wrong, it will not misclassify. That's an assumption that you are inherently making in your mind when you are saying that I should only learn near the failure surface. But that assumption need not be true. And if that is not true, then it will give wrong result. Because Gx was supposed to give a safe, G hat X is now giving a failure. So you are counting a wrong failure point. Correct? Anyways, coming back to what you were saying, which was interesting actually. that X should be such selected such that maximum information is available to the model. How will you decide maximum information is available or not? It is not so straightforward to decide whether maximum available is maximum information is available to the model or not. And that is why all of you are right that step 1 is very important. And in step 1, we will talk about design of experiments. So step 1 is known as design of experiment, DOE. And we'll talk about different design of experiment schemes which will allow us to extract samples that gives maximum information. There are some, the obvious one are that you do a uniform filling. If you do a uniform filling over it using pseudo random number, not quasi, pseudo. Okay, there is Sobol sequence, there is LHS and all of those things. Then the surrogate model generally tend to learn well because it's a uniform kind of grade you are creating. But that is not always true. Suppose the function is very sharp, you will need more point where the gradient is getting changed. So in that case, more points would be there. And there are other ways also. So we will spend a significant amount of time, maybe at least 1 or 2 lectures, talking about only design of experiments, which will tell us how you can generate samples X that gives potentially or hopefully the maximum information to you and to the model, because the model is learning from this. So we will want it to be more informative. Okay, so this step is known as design of experiment or DOE. Design of experiment. There are some usual ones that people have been using like CCD, central composite design, factorial design, and all of those things. But we will talk about them for 5 minutes maybe, whenever we talk about it. And then we go into the more advanced ones, which is sequential experimental design. As I was saying, you can do it iteratively. And in sequential experimental design, we'll talk about sampling, gradient information, uncertainty someone was talking about, all that how can come, and all of those things, and how you can generate samples which will reduce your uncertainty, for example, of your model.
We can use some sampling technique also to sample this.
No. It is very difficult in that case, because if you draw some sampling technique, let's say importance sampling, right? In that case, it will exactly what he was saying will happen. You will get more samples in the failure zone. So it will learn the failure zone, but something away it can get misclassified. Okay. That's what he was saying, right? Area is near design point is same as what you were saying. When you take a Gaussian at the MPP, you get the area actually. You don't get only failure. You get failure and both. Okay. And I will talk about one of the things maybe towards the end of surrogate model, which is a hybrid approach where we will combine this import subset simulation with surrogate model. But that I will keep it for later. Okay. But all of these are valid, by the way. There are techniques which rely on sampling near the failure zone also. There are. Okay. But we will talk about that later. So, but long story short, step 1 and step 3 are the most important points or important aspect that we will be discussing throughout this part of surrogate modeling approach. Some examples of surrogate models. I did not give you any examples, right? So, surrogate model. Some example. So, we will start by discussing what is known as response surface method. That is the first surrogate model that was ever developed. Response surface method. And you will be surprised to know it is nothing but a second order polynomial regression. Now, name is response surface method, and in fact response surface method is also a synonym to surrogate model. It is learning the response surface, the limit state, but it is fundamentally a second order linear regression. Okay. So, we will start with response surface, but there are others also. Polynomial chaos expansion. We will spend significant time on that, at least 2 lectures. Then there is something known as Kriging. Now, this Kriging name might not be known to you. It is after a scientist Krieg from South Africa, who developed this in 1951 for measuring something on the geospatial thing. But the more popular name of Kriging is Gaussian process. So GP. So, we will talk about GP also. Again, at least 2 lectures on GP we will spend. Then there is the obvious one, neural network, which we will not discuss in this course, because that is a course of its own, deep learning. So, we will not discuss about neural network. Then there is something known as radial basis function, RBF. Then there is something known as high dimensional model representation, HDMR. Then there is something known as support vector regression, and you can, by now you realize that all machine learning, supervised machine learning algorithms can come here. Okay. So, I will not increase the list, but fundamentally any supervised learning algorithm can be a surrogate model. Okay. Now, what we will discuss in this course are the followings. In this course, obviously we will not discuss all of that, then this itself will become a course on machine learning. We will discuss response surface model. We will discuss polynomial chaos expansion. We will discuss Kriging and Gaussian process, and we will hopefully discuss HDMR. I might skip that, but other 3 we will definitely discuss. Why these 4 and why not the others? The reason behind selecting these 4 are because these have been used widely for reliability analysis. So, that is why I am selecting those. Also, if I do not cover response surface, polynomial chaos, HDMR in this course, there is no other course that will cover those. But if I do not cover neural network, there is a deep learning course that will cover that. You can always go and check it out. Support vector regression, there is a machine learning course that covers it. You have already studied that. I mean, at least the UG students. What else is there? Yeah, so that is the reason that we are only discussing those which have been widely used in reliability, and you will not get a chance to learn them in any other course. So, that is how these are selected. Okay. And obviously, along with these 4, we will also talk about design of experiments, as I said. And in design of experiments, we will talk about factorial design. So, in DOE, we will talk about factorial design. We will talk about central composite design, okay. And then we will talk about, after this 2, let us see, there is this, no, I will not talk about that. I will then directly go to sequential experimental design with and without uncertainty. So, fundamentally most of the time we will spend on sequential experimental design, because that is the state of the art, and other things are not used that much nowadays, with and without uncertainty. But we will talk about the surrogate model first, and design of experiments we will talk later. Although in step design of experiments comes first, but we will take the opposite route. Okay, because some design of experiments will rely on the surrogate model. For example, sequential experimental design with uncertainty requires that you will have knowledge of Gaussian process. So, that is why we will take the opposite route. So, these are the things we will talk about in this surrogate modeling part of this course, which is like module 3, module 4. I mean, if I can't start from module 0, then module 3. If I start from module 1, then module 4. Module 1 was probability and statistics. Module 2 was form solve. Module 3 was sampling. This is module 4 we have now started. After this, module 5 will be system. Module 6 will be time dependent. Module 7 will be RBDO. So, there will be total 7 modules in this course. 42 lectures, so 6 lectures more or less on an average. It will not happen like that, but on an average you can think of it like that, right? Okay. Any question? So, if there is no question, I will stop here for today. So today was more like a philosophical discussion, no maths as such. But from next lecture again, we will go to discuss one of those things in details, and there you will see mathematics coming back into the picture. Okay. So okay, I'll stop here, and yeah, thank you.